In the last class, we reviewed the foundations of probability or the intuition behind the probability theory. Then we defined the probability space, in particular discrete probability space and finite probability space, and an idea about how continuous theory works. So basically, the probability theory is it's done in two broad ways as a discipline. One way is to consider it as a discipline of pure mathematics, as we are pure mathematics. That's what we are going to do. We define as probability spaces and prove theorems. We don't really care about real life examples. We will see some of them just to work with them. But there is other way of doing this through applying the probability theory, applied probability, but that is to look at random phenomena, happening in reality, and model them with probability. That is by experience. By having a data, you model the phenomenon, whatever happening. Then you analyze the data. I mean, that's also done through data, but that's a new data. I mean, that's a new data which doesn't determine the whole thing. Using the data doesn't say with certainty you cannot say something, but using the data, you analyze it and then come to a conclusion. From previous experience, you assign those probabilities. How that is done, all those things is not, we are not worried about it. We are worried about developing the theory of probability in a rigorous way, in mathematical way. So we define probability space as the following. So we will come to, I made a mistake. I forgot something last time. I will come to that. Okay? So we define the probability space. This is the definition. Read about only finite or discrete probability space, which includes finite. Okay? And which is a finite or countably infinite. So that's what we call as discrete or countable. I mean, countably infinite. Okay. Finite. I mean, countable includes finite, countably infinite, which is a discrete set. Then we take the power set of omega, all subsets of omega. Then P is a function from here to satisfying the property. P of omega is 1, P of empty set is 0, and P of, see, this is the notation I use for disjoint union. When I write like this is disjoint union. That means I equal to 1 to, I mean, this should be what this should work for infinity also. An equal to summation n equal to 1 to infinity P of k. Okay. This means an intersection am means this means is empty if n not equal to. Okay. So it's additive over disjoint union. This is what is called a probability function. Of course, you can take some of them to be empty set. That will give finitely additivity also. That is included in this statement. So last class I said if you take a continuous one, omega is something like 0, 1 or 0, infinity or whatever, a continuous one, then we cannot work with every set. We have to take the subset, A contained in P of omega. You have to take a subclass of the power set. And we called it a sigma algebra, and it's better, it has some of the property. This will be closed under union, closed under intersection. It has empty set, it has omega I set. It should be closed under complement also. I think I missed it. So that's also an important property. Okay? We will come to that later. So for the time being, we will work with either finite or discrete probability space. Mostly finite for the time being. Okay. And more generally, we will define something called random variables in the next class. When the random variables are there, we will mostly forget about the probability space, the omega and all that. Random variable is just a function from omega to real line, something. Or you can take it in some other field also, but we will take real line. So when you have a random variable, this probability space will induce a probability on the range of the random variable, where the random variable is taking the values. So that will give a new probability space. A random variable will give a new probability space. And then I mean, this will be behind the screen. We will not worry about what is omega, what is p and all that. What is this p and all that. So since our probability space is either the finite or countable infinite, discrete, then given, I mean, this p is determined by point mass, or p of p of small p of omega, which is equal to p of singleton omega. This is also a set. So you take the singleton value of that. So if you have p omega, then, or if you have p, I mean, given a p, capital P, like the probability measure like that, then you get a p omega. Or if you have a p, small p omega, then you can define p of any a. You can define it like that also. Summation of omega into a p omega. Okay. This is okay. So this is possible in discrete case. Last time someone asked that instead of this sum we will have integral or something. So this is like probability of a single point. Okay. But in general, if you have a continuous probability space, there the probability of single point may be 0, but still you will have probability, non-trivial probability for intervals. But it's not like you are integrating the point mass or something. You have something else that is called density. Density is a generalization of this, but still it's not the probability of single point. It's something different. There is a difference. Okay. So let's see some properties. So some trivial, we have already seen some. So first one is if you have A, B, two sets which are contained like a two sets, then P of A union B. So we have A union B equal to A disjoint union. So whenever I write this, the union is disjoint, the intersection is empty. Okay, B minus A, okay, which is same as A union B intersection A complement, which you can talk about intersection. I mean B minus A union, which is same as this. Okay. I mean, you can verify that this is equal to this by, I mean, you can write Venn diagram. Okay, you can write Venn diagram. Okay, this is A, this is B, then A union B, this is B minus B is this, or B minus A is also this. You can use Venn diagram to convince yourself, but that's not you should do. I mean, this is a simple case, but whenever we want to say that two sets are equivalent, two sets are equal, then we take a point here and use this, whatever this means. This means either it is here or here. Then we have to prove it either it is here or here, and that will imply that this is contained here. Similarly, if something is here, then it is in one of these things. Then you can prove that, and this is very simple. You can argue it out, but that is how you should prove two sets are equal. You will have more occasions to prove this kind of things, like two sets are equal or something. To prove two sets are equal, you should go logically. Okay, by saying that something is here, then you have the definition and you have the defining this set, however it is defined. You go through the argument and prove that it's also here. Similarly, the other way. Okay, that is how we will prove some set is equal to other set. Okay, say it again. Sorry, it is intersection. I wrote union. Yeah, it's intersection. Okay. So these two are disjoint set. Okay. So because of that, P of A union B equal to P of A plus P of B minus A intersection B. But when A intersection B is contained in B, last class we noticed that if a set is contained, then this set minus is just the minus. Okay, so this implies P of A plus P of B minus P of A intersection. Okay, so this will be, I mean, these are three disjoint. I mean, these are three disjoint set. This. I mean, we are just this minus this. Okay, you can see it from the diagram. Okay. Okay. So we can extend this. If A1 up to AN are some sets in omega, then P of A1 union A2. I mean, we can extend it for 3, for example. For 3, For 3, it is going to be P of A1 plus P of A1 plus P of A2 plus P of A3 minus P of A1 intersection A2. I mean, 2 at a time. I have to write 3 terms. A2 intersection A3 minus P of A1 intersection A3. Here plus it will be A1 intersection A2 intersection A3. This you can prove by taking this union this. These are 2 sets. Use that. And then there will be 2 sets here. See, you want to prove, I mean, I'm saying that this is equal to that. Okay. So this you can prove it. The proof is you can take P of A1 union A2 union A3, which is equal to P of A1. I mean, you use that. Okay. A1 union A2 plus P of A3 minus P of A1 union A2 intersection A3. Okay. Now you will get distributive law A3 intersection A1, A3 intersection A2. There is a union in between. Again, you use that. That will give 3 of that and 1 intersection of that. Okay, this is an exercise. I want you to prove this. I mean, you have to use induction to prove this. Okay, P of A1 union A2 union up to AN equal to. So let me have some notation. It's better to have notation. Okay. Let's have if A1 up to AN are some set. Okay. Omega. Maybe they are equal. There is nothing assumed about disjointness or something. Okay, they are not mutually exclusive. Then S1 equal to summation P of AN. And S2 equal to summation Ij. See, we want to take P of AI intersection Aj. Okay, by taking any 2 I and J between 1 to n, but then we don't want to repeat it. Okay, A1 intersection A2 and A2 intersection A1, they are same. So we don't want to repeat it. So we use this I less than or equal to J, less than or equal to n, greater than or equal to 1. Okay, we take 2 of them, but we make sure that I and J is not, Ij and Ji are not repeated. Okay, so this is S2. Similarly, Sk equal to summation 1 less than or equal to I1, I2 up to Ik less than or equal to Ik less than or equal to n, P of AI1 intersection, AI2 intersection Aik. This is Sk. Then P of A1 union A2 union up to union AN equal to S1 minus S2 plus S3 minus S4. So this will be, generally it will minus 1 power k plus 1 Sk, okay, plus up to minus 1 power n plus 1 Sn. Okay. Whatever. You can prove this by induction. If I prove, it will be messy. Okay, it's better you sit down and prove it. Shall I give it as an assignment? Okay, this is an assignment. Okay, you sit and prove it. You assume it for n. For 1, it's clear. For 2, is clear. For 3, is clear. So up to 3, we have verified easily. I mean, you can verify easily. You don't have to prove it for 3. It's enough if you prove it for 1. But I mean, we have proved it for 2. So now assume it for n. Then for n plus 1, you take up to n. Then you use this formula. Okay, 2 formula. Then you get something, but you have to write this expression mathematically, and there will be something messy. You have to get the result. I am sure you are very used to this kind of induction, using induction. So using that, you will get it. Okay. So this is assignment number 1. So there are 2 kinds of assignment. Some few assignments I will give it in the class. You have to remember and do it. Few things I will post it in the Moodle. So you have to do it and submit. Okay. If you don't come to the class, you ask your friends to. I mean, it's better you come to the class and note the assignments. Okay. Huh? No, you have to submit. Class assignment, Moodle assignment, both you have to submit. There will be marks for that. So I want, I mean, before midsum, I want to get it before midsum. So within 2 weeks, 1 week or something. Okay. You can post it in the Moodle. I will give you a link. Or you can give it to me. If you write it in a paper, you can give it to me in the class. Say it again. Yeah. For the class assignment also, I will give you a link in the Moodle where you can submit. Okay. Or you can submit it directly to me if you write it. If you type it, you submit there. Okay. Everything is in PowerShell. What else we are dealing with? It's all PowerShell. There is no sigma algebra. We are dealing with discrete case. No, this is generally true, but this is generally true. I mean, as far as you can see, the reason for using sigma algebra and all that is you cannot make sense otherwise. Okay, you want to define a probability measure. It cannot be defined on the whole of PowerShell. So that is why you choose a subclass. Okay? So when you can do it, these things are true. This just goes with the axiom that this axiom only. Okay, this is true whether it is continuous or discrete. There is no difference. Okay. Let's work out an example problem. I mean, I'm not very comfortable with combinatorics and other things. I mean, I'm not a probabilist, and I mean, combinatorics is not my. I'm not very comfortable with that, but let me try. Okay? So the problem is the following. Yeah, let us slightly complicate the problem. Example. Okay? So rolling a die n times. Okay? So one thing is you can write the probability space explicitly and work with that if you want. Okay, that's not necessary. Okay, I mean we should do whatever is comfortable for us. Okay, we shouldn't complicate it too much. So when the probability space is not necessary, when you throw a dice and all, it's clear. Okay, when you throw a dice, you assign probability for each number to. I mean for each number to come, you assign a probability 1/6. It's a equal probable. Okay, so we know what is the probability and all that. So we will do a calculation. I just want to use this formula, so that's why I'm using it. Okay, so you roll a dice n times. Okay. N times, and we want to calculate the probability of probability of all faces show 1 to 6. Okay? At least 6 times you have to show. I mean, you have to throw the dice, otherwise it's not possible. All faces 1 up to 6. Okay, 1, 2 up to 6 shows up. Okay, you want to find this probability. Okay, so how do you find it? So first you want to show. I mean, this is just the intersection of first phase. I mean, in the you have thrown the dice n times, and you want to find the probability of all. I mean the probability all the phases. I mean, at least once this phase should show up. Okay, all of them should show up. So the complement of this. So let us A equal to this. Okay? All phases show up. Okay. Then A complement. What is A complement? Five or less of phase. Yeah. So in other words, at least one phase doesn't show up. Okay, that's what the complement is. So you should be. I mean, I'm sure you're comfortable with this. You should be careful with all phases show up. Doesn't mean that the complement is not all of them. I mean, it's not possible. Okay, so at least one phase does not show up, right? That's not true. Okay, so let us call Bi equal to phase I does not show. Okay? In the n1. So what is the we know probability of Bi? So only 5 of them should come up. Okay, so each one 5 of them should come up. So probability of Bi in n trials. Okay, you are throwing the dice n times. Probability of Bi is what? 5/6 power n, right? Is correct, no? Okay. The first one 5, second one 5 by 6. So n times 5 by 6 power n, right? So we want to calculate probability of this one, this probability of A complement. That's what we want to calculate. Okay. Then probably, which is equal to probability of union of BI. I equal to 1 to 6, right? Union of BI. So now you use that formula, which is equal to summation probability of BI, I equal to 1 to n, which is same, of course. Then summation I less than j, less than or equal to 6, greater than or equal to, every choosing 2 at a time, right? So P of BI intersection BJ. Similarly, you take 3 at a time and something like that. Okay? Sorry, this is minus, this is plus. Okay. Then there is plus summation I j k, probability of AI intersection AJ intersection EK. 3 of them, less than or equal to 6, greater than or equal to 1. And minus and goes on like that. Which will be, I will just write the result, which will be 6, no, n. I mean, choose one at a time, n1, 5 by, I will just write the answer and explain you, okay? Power n minus nc2. So nc2, 2 of them should not occur. So 4 by, I mean, 2 of BI intersection BJ is I and J should not occur. So remaining things are 4 by 6. Power n, right? 1 to, sorry, 1 to 6. Huh? Say it again. Where are you saying? Here, huh? No, here NC1. No, you are choosing 1. You are choosing I. 6C1. Sorry. That was, yeah. Sorry, N is our 1. Okay, yeah, that's what you are saying. Correct. 6C1. I was only worried about 1. Okay, yeah, 6C1, that's right. Similarly, 6C2, 4 by 6 power n, plus 6C3, 3 by 6 power n. Go on like that. And finally, 6 is even. So it should be even things are minus, right? So 6, which is 1, of course. Then 1 by 6 power n. You just calculate this. This is probability of A complement. So probability of A is 1 minus. Okay? And it will start having, this will start having positive value only after 7, right? After 6 or something. Okay? Anyway, you work with this. Is okay, no? Yeah. Six is 5, no? You should choose 5 of them. Yeah, right. It should be 5. Not 6, yeah, it should be 5. Yeah. Then it will be a plus, right? It will be a plus. Yeah, you should be more careful about these things and you should work it out. Okay. Okay. So this is where we have used this. And we can write some inequalities. So sometimes it may not be possible that you may be able to compute this when n is large or something. This A1 union A2 up to this. Okay. But we have this subadditivity. So this is clear that probability of union I equal to 1 to n AI is less than or equal to probability summation I equal to 1 to n P of AI, which is what we called it as S1. Okay. S1. Okay. This is just clear, right? Because I mean, you have something you have to prove that is positive. That's one way you can do. This is because probability, I mean, you can define, we have done this here, Pi equal to A minus A1 union A2 union up to AI minus 1. You just remove the previous things. Okay. Now probability, so then probability of union of I equal to 1 to AI is equal to this or this joint. Okay. BI intersection, I mean, the BI intersection BJ is empty. And the disjoint union of BI is union of AI. Okay. So this implies probability of union of I equal to 1 to n AI is equal to summation probability of BI. But BI is a subset of AI. Okay. So this is less than or equal to summation P of. Okay. This property is what is called subadditivity of probability measure or function, whatever you want to call it. BI is AI and you remove all the other sets, all the sets before that. Yeah. What is that? No, A2 is A2 minus A1. A3 is A3 minus A2 and A1. A2 union A1. What's the problem? I minus 1, yeah, up to the previous one. Maybe, I mean, for first one, we don't do anything. When I not equal to 1, for I greater than 1. Yeah, I mean, A0 is 0. A0 is empty if you want. What is the problem? You remove the previous one, I'm saying. Yeah, so that they will be disjoint and you can write this. Okay. And further, it is also true that probability of union of I equal to 1 to n AI is greater than, this is less than that S1, but it is also less than or equal to S1, greater than or equal to S1 minus S2. Okay. We can prove it by induction. Okay. And I mean, for other things, it's true that up to K, you can, I mean, it will be between, oscillate between the, I mean, it will be, then again, P of union of I, so this is also P of union of I equal to 1 to n AI will be less than or equal to S1 minus S2 plus S3. Okay. It will be oscillate between them. You can prove it, but that will be getting more messy. So I asked you to prove this. This is the assignment. Okay. I think it should be easy. You can use induction. It will be clear for proof. Then you can use it for induction. Use induction. This is less than this. BI is contained in A. Contained, yeah. So we have proved that monotone property last time. If A is contained in B, P of B is greater than P of A. Because of, okay. So this is assignment 2. I mean, it's just to work out, I mean, work with sets and prove something. Okay. So assume it for n and prove it for n plus 1. That's all. Okay. So now we want to introduce some, go to your next topic. You must have heard it in your higher secondary school, I'm sure. When you write all this competitive exam, you must be knowing this. This is what is called, but we will conditional probability. Okay? But we'll do it again. So what is conditional probability is, of course, you do an experiment, you include all possibilities, okay? But then you know that, I mean, the experiment may be very general and you don't, the experiment a priori, you don't know anything, but now you know something has happened. Okay, then you have to update your probabilities. Okay, you have to change the probabilities because you know something. Okay, so you are updating the probability space. So since something has happened, that will originally have a probability. Now the probability of that will be 1, right? Because you know it has happened. Okay, you toss a coin, you take a pack of cards. Okay, and there are two events. One is whether it is a spade or something. That's one thing. The other one is whether it is a ace or that's one thing. Now you know that it's spade. Now you want to ask the ace spade. What is that? Initially, the probability of getting a ace spade was 1 by 52. Now it has become 1 by 30. Once you know it is it's a spade. Okay, so your probability becomes something. The probability gets changed. Okay, so that is just updating the condition, updating your probabilities. That is, in other words, you have initially one probability space. Your collapse initially your probability has omega. Okay, now you know that a subset of omega, which is a proper subset, which has happened. An event means that's what an event is. You know something has happened. Okay, a has happened. So your omega should become a. Right? That's what you should do. So what will you do is you will become a new probability space. And if P is the original probability space, you will define a new probability space such that Q of A equal to 1. Q of A equal to 1. Then all the other probabilities, suppose if I have a B, another event in omega, you know that B intersection A has some probability to happen. B intersection A complement has no probability. Its probability is 0. Okay. So true probability B intersection A. Q. Okay. So how will you define that probability? So suppose, so again I will go to our experiment of doing n times and what happens. Okay. If you do an experiment n times, this is just our intuition, n times. Okay. Suppose NA is the number of times some A happens. So NB is some other event B happens. Now you know NA has, now the probability of A is usually, this is not probability. This is how, this will be close to our probability or whatever. This is our intuition probability. That will be NA by N. Okay, this will become the, if you do N becomes infinity or something, this will become your probability. And NB by N will be the probability of this. But when you know A has happened, the probability of NA will become, A will become 1. And probability of B should become NB. NB intersection A divided by NA, right? If you know A has happened, among A, what are the B's, which is the intersection, and you divide it by the total number of B's. Okay? This will be the that. But this is actually equal to NB intersection A divided by N, NB, NA divided by N, right? So which will be like probability of P intersection A by this. See, the conditional probability is something, you don't change the probability space. Within that you work. Actually, you have to change the probability space because you know something has happened. You have to completely change your probability space and your omega should become A. So you do that. Because why you don't do that? You just want to work logically. You don't want to assume that A has. You because you want to use some other formula, base formula, and other thing. So you know the probability of A given B. Then you want to compute the probability of B given A. When A has happened, there is nothing like B given A. There is nothing like you are assuming that. It is just you work logically. Okay? Because you want to go through compute something. It is sometimes easier to compute A given B than B given A. Then using that you want to do something. So it's because of that you want to go mathematically. So that's why in real life, A has happened, then A has happened. That's all. There is nothing like that. But so we are not we are not collapsing the probability space to A. Instead, we work in the same probability space and we define something called conditional probability, which is like, this is the conditional probability, which is like our, working within the, which is like collapsing the probability, okay, which is the new probability, like new probability, but it is not the new probability. It is just a new concept, new definition. So this is the definition of conditional probability. So we have probability space, omega, everything behind. Okay. Then you have A, B, two subsets contained in omega. Okay. This is for discrete case. This will work for continuous case also, except that this AB should come from the sigma algebra. Okay. That's all. I don't want to use sigma algebra each time since we are actually using finite probability space. So I don't want to complicate it. So A and B are that. Then the conditional probability, this is what is the conditional probability. the conditional probability of A given B. Given B has happened, which is denoted by probability of A given B, which as we have defined, probability of B, okay, you divide the whole probability by B, then P of A intersection B. That's all. This is the definition. You don't have to worry about your intuition. This is the definition. We will work with this. Okay? This is just the conditional probability of A given B, which is just probability of A intersection B divided by P of B. That's all. Okay. This, do you remember any physics phenomenon where this collapse happens? Yeah, quantum mechanics. But you can't use that there. Okay. The reason is there is something called commutativity, which is here, which will not be there in quantum mechanics. So there you need to do something else. Okay. The collapse uses something else. You will not just take this conditional probability like that. You have to use a projection, something. Okay. So, something like that. Yeah. You have to project it onto something. This will not exactly what this concept will be generalized there. Okay, in the collapse thing, if you do a measurement in quantum mechanics, the whole thing collapses to something. That is where actually in reality, nature works with probability. That's what we think. We don't know. Okay, that is just our interpretation. Okay, so there it's not exactly like this. Okay? There is some difference because what we do, the probability is whatever the probability we do is actually commutative in the sense that the random variables commute, whatever we are going to define. But the random variables will not commute in quantum setting. Okay, so we have to use something called quantum probability. Okay. So this is the definition of conditional probability. Shall I give an example? Okay, I will not calculate everything. I will just give an example and then let's just do that. So yeah, maybe. So this is example. This is more or less same. I mean, I'm following this book. Okay, I'm not exactly following this book, but this is our reference. Okay, I said it in the last class, but after the class, maybe some people didn't notice. OL, port, PORT, right? So theory of probability, elementary theory. I don't remember the title. Okay, that is the title of the book. You just, I mean, there are two books by them. One of them. Okay, there is another one is stochastic process and something. This is the probability, elementary probability theory. So that's what we will refer. And not everything. Stone, port, PORT, R. I tried to write 2 times. This is the best I can get. Okay. I tried to write the R some 2-3 times. Okay, this is what I got. Port and stone. Okay, so this example is from there, but there is some smoking and other things. I mean, here in India, I mean, how many male smoke, female smoke, or something. But in India, it's very hard. The probability is too high for India, so we will do something else. So we don't want to use that for. So suppose we take a CMI classroom, okay, a class DSC classroom or something. This is also not very realistic, but let's hope that this will become real. A class, CMA class. So suppose say some 40% girl students, boys, okay, let's say boys, okay, and 60%. Hopefully, it will happen sometime. Okay, so this will be girls. Okay, 60%. Huh? No, it will happen sometime. Whenever, It's okay. That's okay. I mean, let's hope for the best and see. Okay. Okay. We will. Let us be politically hopeful. Not politically correct, but politically correct means I have to say 50-50. So this is politically hopeful. Okay. Hope for one day they dominate you or something like that. Okay. So 40% boys, 40% girls. And let's have the example that so among them, among boys, some 30% are 30% computer science. Okay, the others are physics. Okay, and among girls, among boys, okay, Huh? Which is also too much, no? 80% plus physics. Yeah, I'm always unrealistic. Okay, it's okay. Here there is no politics involved, but it's okay. Okay. Among girls, 50%. Okay, 50% computer science. I know all of you are computer science. There are five, six of them. Six of you should be physics, I believe. Okay, okay, you are physics. Okay. So since you are talking about collapse, okay. So what do you want to do? Now you select some one person at random. How do you select? Of course, if you can ask them, but this is an experiment. So you have a answer sheet or something. You know that the selected person is a computer science person. Okay. Then you want to find the probability that it's a boy or girl. Okay. So how will you do that? So probably so from here, let's call this as B, this call this as C, and so G, call this as C, and the physics one is P. Okay. Physics P. Okay. Now probability of B is directly given, which is equal to 4 by 10, which is 0.4. And probability of G is 0.6. Okay. Now what is given is probability of C given B, right? Which is 0.3, right? And similarly, probability of C given G is 0.5. Okay, suppose. Okay. Then you have selected someone who is computer science. Okay, that is probability of C. You got someone as computer science. You want to see whether it is a boy or this is one. This is what you want to compute. Okay. Okay. So how do you compute? So this is what I want to compute. I think I should have recalled something. I should have wrote some formula. Yeah. So I thought base rule is not needed for this, but let's see. So probability of B given C is equal to probability of B intersection C by probability of C. Okay, we don't know what is probability of C yet. So, okay, so I need this proposition. I'm sorry, I should have done this earlier. We need, I mean, this is just not proposition, which is remark or something. Okay. So given, I mean, the A, B, I mean, we have omega, we have probability measure and all that. We have first, I mean, this is just remark. Okay, remark. These are all very easy consequence. Remark. So our definition is probability of, I have you said A given B equal to P of A intersection B by probability of B. Okay. This implies probability of B times probability of A given B is equal to, I mean, I'm writing it like this because I may get confused. Okay. So that's why I'm repeating it, the same thing, probability of A intersection B. But then this is also equal to, you can write it as probability of A times probability of B given B, right? You can write it like that. Okay. Now, if you have two sets, A and A, I mean, two sets mean A and A complement, suppose. So probability of any set, probability of C is equal to probability of C intersection, so B and G, right? There, but for any set A, P intersection A plus P of C intersection A complement. Okay. So that is equal to probability of, we know C given A times P of A, probability of C given A complement, P of A complement. Okay. Using this formula, you can write this. I mean, here A, B are general sets. Okay. This has nothing to do with this example. In this example, this will be P of B intersection C, even B intersection C. B intersection C also we may, so this is equal to, sorry, this is just B of B of B of B, you know, so P of C given B. So similar, but here P of C. Okay, this is equal to P of B, P of C given B, and here P of C you have to calculate. So that is what we use this formula. P of C given B, P of B plus P of C given G, P of G. Okay, all these things we know, right? So you can calculate P of this and this. So that's what you have to do. You'll see more example of this. Okay. I will write a more general formula. So whatever we have written is, if you have two set, if you want to compute any C, any probability of any set C, that is same as computing probability of C intersection A plus C of C intersection A complement, that is equal to this. So this is our formula. P of C equal to P of C given some C given A times P of A plus, I'm just writing it again, P of C given A complement times P of A complement. Okay, I mean here G complement is B, and in that example. Okay. Similarly, if we have A1 up to AN, okay, such that AI, they are mutually such that I write it like this. Okay, then the disjoint, I mean, then the pairwise disjoint, okay, I equal to 1 to N equal to omega. Okay, mutually exclusive, exhaustive, something. Okay, their union is everything, and they are mutually disjoint. Okay. Then P of any set B equal to, as you can see, P of B intersection AI union of I equal to 1 to N, P of B intersection AI. Okay. Now that is equal to P of summation P of I equal to 1 to N, because they are disjoint, A's are disjoint, so the intersection, those things are also disjoint. Summation P of B intersection AI. And use the same formula, summation I equal to 1 to N, P of, we know P of, yeah. Now, if you want to compute P of, I'm going there. So, so okay, we will move to some. Now we will move to 202. Next time on. Sorry, you couldn't see. Yeah. Yeah. These are all you should be able to verify yourself. Okay. These are all you. I mean, this is just usual 8th standard algebra. So algebra used is 8th standard. The idea is whatever. Okay. Yeah, 11th standard or something. I mean, it is just plus or minus. It is just usual 8th standard algebra. I said. Okay. So I have to do it one by one. I'm just doing it. Okay. There's nothing complicated than this. So P of AI given B. Okay. You just write it. It's same as P of AI. I mean, if you have something like this, AI equal to omega. Okay. If you have some mutually exclusive exhaustive event AIs, such that AIs are disjoint and the union is omega, okay, then P of AI given B is P of AI intersection B times P of B, okay, which is equal to P of B given AI times P of AI. Okay. Then summation, I'm using a different index because AI is here, J equal to 1. P of B given AI, P of AI. Okay. Suppose if you know P of AI and P of B given AI, okay, then we can compute P of AI given B. Okay. This is what is called base formula. I'm sure you know this also. Okay. I mean, if it is not taught in your higher secondary, I'm sure you should have studied for your competitive exam. All of you must have written. Okay. Okay, this is base formula. So we want to use this for some example. How much time we have? Okay. So there are in the book there is something called Polyos ans. I mean, uh, only one book I said. There are 3 people have written one book. There can be 3 authors for a one book. One book, only one book. Okay. So that has a lot of examples. It's enough to read that book. That has a lot of exercises, and you do that, and that's enough for you. Okay. But I will not ask from those exercises. It's just for your practice. Okay. Okay. Assignment I may give from that. Okay. So let's first do the following example. I thought about 4 examples I should remember. So the first one is, I may not have time for that, but let's see. The first one is have a pack of cards. Okay, your pack of cards. That's so. I mean, I didn't write omega all those things. If you see all, I mean, in all these examples, because that's waste of time. Okay, we know what is omega, and you can write it if you want. For example, in the, but it's difficult to write for this boys, girls. You need not list down all the boys. You need not list down all the girls. Instead, you can write BC, BP, GP, GS, right? You can just consider 4 elements because you don't care about, I mean, the group. It's only the group which matters. You can work with 4 elements if you want. I mean, that is the probability space. Okay? That has, each one has a probability which you can compute. Okay. So you have a pack of cards and you removed one. Okay. So our omega is pack of cards and one card is removed. One card is removed from a pack of cards, from a pack. Okay. You don't know which card is that. Okay. Then you select one card from the remaining 51 cards. Okay. So you want to calculate the probability of getting a spade. Okay. So originally, what is the probability of getting it? When there are 52 cards, the probability of getting the spade is 1/4. Okay. So now you have removed one card, and you don't know which card is that. Now we want to compute the probability of the spade. Okay. So let us have our A be the event that the removed card is the card which is removed. The removed one is spade. Okay. So that is like selecting a card from pack of cards. So the probability of the removed P of A is 1/4 again, right? P of A is 1/4. And of course, P of A complement is 3/4, of course. Okay. We have a pack of cards. One card is removed at random. We don't know which one is that. From the 51 cards, we from the remaining cards, calculate the probability of getting a score. Okay. One card is removed. Okay. And one card selected from 51 cards. 51 cards. Okay. The selected one is spade. The selected is spade. Okay. We have a pack of cards, 52. One card is removed, so 51 cards are there. And from there, you select one card. This is not removed card. You select card. Okay. That card is spade. What is the probability of that? Okay. So now we know that removed card is spade. That has probability 1/4. Okay. P of A complement is 3/4. Now we want to get a spade. So now P of S, which is the getting a spade, call this as S. Okay. This set is S. Selected card is S, is spade. Okay. Now P of S is equal to P of S given A times P of A, right? express P of S given A complement times P of A complement. We are using this formula. Okay. This is not clear. Find the probability of select. We have 52 cards. One card is thrown out somewhere randomly. You have 51 cards now. From there, you select a card. Okay, that's why I use a different word. Removed card, select card. The selected card is paid. Probability of that. That's all. Selected card. Yeah, you select a card. Yeah, selecting a card. Yeah, correct. Okay. We don't know. This is conditional probability. You want, so this is how we use those formulas. That's what I'm saying. Okay. This is just mathematics. You don't ask real life questions. How do we know or something? If that is done, then this happen. Okay, both the same we assume and we go by logic. Okay, logic will be weirder than reality most of the time. Okay, so this is logic what we are using, not what happens in the real life. Okay, once you know this is A, then then it's clear the other one is absurd to consider the other one, but we consider those things. Okay? So yeah. So now we want to find A, which is the removed card is paid. That is A. Okay? That is one thing. Whether A could have happened, A complement could have happened. A has probability 1/4, A complement is probability 3/4. Now you want to find P of S. S is the selected card is paid. Even though my handwriting is not right, I have written everything. Okay, all the information is here. If you carefully look at it. Okay, so now we want to calculate P of S, which is by our formula P of S given A, P of A, P of S given A complement, P of A complement. We know all these quantities. Okay, that's what I'm going to write. So P of S given A, when the spade is selected, okay, selected card, when the removed card is paid, okay, then there are remaining cards, among them 12, 13 minus 1, 12, no? 12 spade will be there. So P of S given bed is 12 by 51, right? 12 by 51, correct? Into 1/4, into 1/4, which is the P of A is 1/4. Similarly, now spade is not selected, then 13 by 51 into 3/4. We just calculate this. 1/4, you take it out, then it is just 12 plus 13 into 3, which is again 51 by 51, which is 1/4. So you work with the 51 cards, you again get 1/4. This is the beauty, whatever. You can go on like this. You can again remove something. You can go on like this till you get 4 things or something. Okay, you can try that. Okay, I'm not giving it as an assignment because I'm going to give a similar problem as assignment. So this is like coming down. Now we will add something and consider the probability. The probability will remain same. Okay, that is our problem, which is called Polyon's scheme or something. Is there any other way? Why do you want any other way? This is very easy. You may be able to do. These are all combinatorics. You may have to argue, but this is some easier way of doing it. Okay? We do all this conditional probability because we don't want to get confused with combinatorics. Okay? You have to consider. You have to list down all possibilities. Okay, the number of possibilities. You can do that. It is just you can do it. Okay, you can list down all the possibilities, 50, whatever. Then you kind of calculate how many times this happened, how many times this happened, just divide it, you will get it. That's one way of doing it. Okay? But then this is easier. You do it immediately, right? So this is in the book I said. This is not in the book. So this is example. This has a lot of application. Okay. URN. Okay. URN scheme. Where is he? Polya is a name. He's a probabilist. He is a probabilist. He's a person. URN on scheme. Scheme. Okay. Okay. I can change this. Hmm. Okay. This is as follows. You have a on URN. This is a R. Okay. Is it too difficult to find it? On contains R red balls. Okay. And B blue balls. You can take different colors if you want. They are all identical and all that. So probability will be 1 by something. Okay. There are R red balls and on B blue balls. Okay. One ball is selected. Okay. So one ball is selected. If it is red, you add some C number of red balls into it. If the selected ball is blue, you add C number of blue balls. Okay. So one ball is selected and C number of selected color is added. Okay. Then you want to calculate the probability of getting a red ball in the second time. Okay. When you draw another ball, getting a red ball in the second draw. Okay. You select a ball again, second time. Yes, everything is put. Okay. So I will write it, it will be clear. Okay. So initially there are R plus ball, R plus B ball. So getting any ball is 1 by R plus B. Getting a red ball is R by R plus B. Okay, initially. Now C balls are added, whatever. Okay. Then you get, then whatever, the same color. Then the ball is taken. Okay. So let's take R1 getting a red ball in first draw. Okay. First time. Similarly, R2 getting a red ball in second draw. Second draw. Okay. Similarly, B1 and B2. We can calculate B2 also. Now we want to calculate getting about R2. We want to calculate probability of R2. Right? Okay. So probability of R2 is probability of R2 given R1 to probability of R1. Right? Plus probability of R2 given B1 the probability of B1. Same example. It's something, same thing. Exactly. It's going down from a pack of cards, it's going increasing on. Okay? Yeah. I want you to do the nth one. Assuming n, do it for the n plus 1th one. Okay. It's the same thing. Okay. Just I want you to make sure you all understand that. Okay. So, okay. So now what is P of R2 given R1? R1 has happened. Okay. So it becomes BR plus B plus C. That R and R plus C. There will be R, C balls are added, but C balls are red balls if it is R1. Okay. Times P of R1, which is R by R plus B. What? R minus minus 1. No. R plus C. No, it's no minus 1. C balls are added to that. One ball is taken with them with that ball. Let's not, minus 1 is not going to change much. Let's not complicate it. The idea is to get the same probability. Okay. Take ball, put it together. Yes. Yeah. With C balls, you put it together. It is just selected, not removed. It's selected and the same thing. Everything is put back. Okay. Plus, so now the blue ball is selected. So R by R plus B plus C. Okay. Now this is B by R plus B. Okay. You take 1 by R plus B outside. Then if you add it, it will be just R by R plus B. Probability remains same. It's the same example. It is just they're just going upward. Okay. Now assignment is in the nth draw also it remains the same. You have to use induction, of course. Okay. So that's the assignment. I mean, it is done nth time, n minus 1 times c balls are added. In the second time, c balls are added. Then again something happened, and I mean, the nth time you have n minus 1 c balls are added, but different colors. Each time something is selected and something happens. Okay? You read the book, it will be clearly written. Okay, if you have doubt. So this is assignment 3. Compute P of Rn. That is getting red ball in the nth time. Okay? And it's similar for B, so you don't have to do. Okay. That's about conditional probability. We have written Polya's thing. Say it again. Yeah, we have 10. Probability of no. Yeah. What are you saying? If you take something and put blue balls, that will not be the same. That's not the point. You don't know which one you are putting. Whatever you are getting selected, you are putting it. That's the scheme. Okay? If you get red, you put red. If you get blue, you get. So that's why the sum is there. Okay. So let's final one. There are 2 more examples. Maybe we'll talk about it later. Okay, if it is important, if there is some difference. Let's discuss what is called independence. Yeah, shall we continue? Okay. So A is one event and B is one event. We say A is independent of B if conditional probability of A given B. You know B has happened. That has no impact on A. That is what is independent is. Okay. So that is you want to have P of A given B equal to P of A itself. But then this is equal to P of A intersection B divided by P of B. So this will be equal to P of A intersection B equal to P of A times P of B. So this is our definition of independence. I mean, this is just heuristic. So this is the definition. Okay. So A, B, 2 events are said to be independent if probability of A intersection B is P of A intersection P of B. Okay. This is what is called independence. Huh? Huh? P of B, sorry. I hope I wrote it right correctly there. P of A into P of B. That's what I want to write. I mean, I have written the same thing. Okay. Yeah. P of A intersection is P of A times B of B. Okay. So heuristically, I mean, we may think that some things are dependent or something, but you can see that something is not. It's not like that. So you throw a dice twice. Okay. So dice thrown twice. Okay. Then, so one event A is getting even first draw in the first throw. Okay. B, sum of the 2 throws, sum is even. I mean, there are 2 times the dice is thrown, the sum is even. Okay. You will think that these 2 are not independent because first one is even, then there are only 3 choice. Initially, the sum is even means there are 6 choice. Something you can take, something odd and odd, even and even you can take. But once it is even, it's only even. But these 2 are actually independent according to this definition. You may think that they are independent, but we have to work with definition. According to this definition, that is independent in this example. Okay, because you can compute P of A intersection B. So P of A intersection B. That is, first one is even, and the sum is also even. There are totally 36 choice, 36 possibilities. P of I mean, if a die is thrown twice, there are 36 possibilities. 6 into 6 is 36. Okay. Among them, so P of A equal to, I mean, first one is even is, I mean, 1 by 2, right? 1 by 2, no? And P of B 1 by 2, huh? 1 by 2. Now P of A intersection B, the first one is even, the second one is, so that you have to choose only even from here. That is 1 by 4, right? Hmm? Is it right? From the total number of events, it is 1 by 4. P of A intersection B, it has to be even here. So it has to be even here also. The second one is also even. Both even is 1 by 4, right? Okay, 9, there are 9 possibilities. 9, no? Yeah, 9 by 36 is 1 by 4. So P of A times P of B equal to P of A intersection B. So they are independent by this definition, even though it may look that they are not independent. I mean, you may think that they are not independent, but the definition is what is important. So it's, I mean, your heuristic, I mean, your intuition may not be right. Okay. So this is an example. So this is the definition. Okay. Okay, we don't have much time. So I will just define for n events what is independence and give a counter example for that. So if you have some A1, A2 up to AN, okay, said to be independent, if you take any subset of P of AI1 intersection AI2 up to AIK, okay, where I1, to take this set, I1 up to IK is a subset of 1 up to n. Okay? To take some k elements from there, this is equal to P of product. How do you write product? This is okay, no? Product. I equal to 1 to k, P of 1 to k, P of A, I, k. Okay. So this is what is called independent. So counter example, very simple example I will give. For pairwise independence does not mean independence. Okay. Pairwise means this intersection is satisfied for two of them. Okay. Pairwise independence does not imply independence. Okay. So we consider, yes, I mean, you can condition and you can consider the conditioned probability space, right? You know something has happened. So our probability omega is, you tossed 3 times and you got head twice. Okay? You know head has, no, not head twice, head has come even number of times, either 0 or this is your probability space. TTT. You can take any probability space, any probability, I mean, it doesn't matter. It need not be consistent with the reality. Okay. You take this as your probability space and you assign the same kind of probability, 1 by something or whatever. Okay. TTT and T, H, T, H. I mean, this is head tail. Okay. And T, H, H. These are the 4 elements. Okay. And AI is getting a head, H, in the ith toss. Okay. Getting a head in the ith toss is AI. Okay. then probability of A1, A2, A3, or the probability of all these AI is getting a H in the ith one, which is 2 by 3, 2 by 4, 1 by 2. Okay. Probability of AI intersection AJ, which is like getting a head in I and J, both the places. That's what AI intersection AJ. You have to get in the ith place, you have to get in the jth place, where I not equal to J. Okay. AI intersection AJ. Okay. So that is just, I mean, getting I in the 1 by 4, right? Which is equal to P of AI intersection P of AJ. Okay. So they are pairwise independent. On the other hand, the set itself, A1 intersection A2 intersection A3 is empty. The probability should be 0. And on the other hand, P of A1 times P of A2, P of A3 should be 1 by 8, which is not the case. Okay. So pairwise independent does not mean they are independent. I'll stop here, I'll continue.